No problem. Anyway, good morning, everybody. Today is May 20th, and we still have, actually today we have a chapter 27. Chapter 27 deals really with the stars and galaxies. We still have one more chapter after that, with chapter 28, and that deals with the structure of space-time and the entire universe and modern, basically, view and perspective of astronomy and cosmology, basically the evolution of the entire universe. So the entire universe as basically as one topic. We'll touch a little bit about that in this chapter, but we're going to leave the main bulk for it, for the observable universe and non-observable universe, and basically the entire size of the universe is another topic for chapter 28. Anyway, so let's share. So which means that on Thursday, a week from today, we really don't have a class unless one of you or some of you want to meet. That would be fine. I'm available. And then after that, it's when well, let me look at the assignments. We have on June 2nd, the exam review for exam 4 is due. On June 3rd, which is the day after, what is June 3rd? It should be Tuesday or Thursday. June 3rd, which is a Thursday, that is when exam 4 is due. And then June 7th, which is the Monday after, is when we're supposed to have our final review also is due. And then June 8th is going to be our final exam for this class. So this is basically what we have laid out for the entire course right now, which is the remaining of the course, basically, in terms of what needs to be done. So don't forget, we have an assignment due May 31st. Let me change the date on that. I don't like May 31st because of the fact that May 31st is actually a holiday. So I need to change that to the next day after that, which is June 1st, okay? So that you enjoy your holiday on the day. Okay, so let me share with you the screen of what we are supposed to cover. If I can find it, share. Again, today we're talking about stars and galaxies. And what we'll be covering is basically the night sky, the brightness and colors of the stars, and how they are related, basically. No, Corin, okay? That's in a nutshell to answer your question, okay? Unless you want to meet for something, that's fine then. We can talk about it later on. Anyway, so basically the color of the star, and we have seen that when we were talking about the black body radiation, basically that if you take a spoon and you heat it up, as its temperature rises, its color starts to change. The less temperature is actually around red. And then as the temperature increases more and more, it's going to shift toward higher and higher frequencies, in this case, more energetic electromagnetic radiation. So that was a connection. That was, if you wish, a very important parameter. So if we go outside now and you look at the night sky, and you see a star and you see it reddish, then you know its surface temperature is less than a star that is bluish, for example, color. So stars that are blue, and this is one of the questions that you might have in exam 4 or even some of the times in the final, is that there is a correlation between the color and the temperature, the surface temperature. So that is basically what the point is. As a matter of fact, the HR diagram, Hertzsprung-Russell diagram, is really exactly this. You classify the stars based on their colors and their temperatures and their size, okay? And when you look at those stars, you see that there is a clear distinction between 4 groups of stars, really. There is the ones, first of all, the main ones, the bulk ones, they sit on a diagonal line. And those diagonal lines are called the main sequence stars. Those are stars that are in their normal life cycle, like the sun. As a matter of fact, the sun is taken as a reference, okay? The size of the sun, the temperature of the sun, not the temperature more so, but the brightness of the sun is taken as a starting point. There are stars that are less bright than the sun, and there are stars that are brighter than the sun. There are stars that are smaller in the sun. For the vast majority, they are smaller. The bulk of the stars are smaller than the sun. And there are a lot of stars actually that are also much, much bigger than the sun. The sun dwarfs in comparison to their size. This is basically the main sequence stars. The main sequence stars, what happened, if you look at their activity inside, you will see that all of the activity is happening in their cores. And what they are doing actually during their main life sequence, basically stage, is they are converting hydrogen inside their core into helium, producing energy for that, okay? Depending on the size. If there is more stuff in the sun, the star, like for example, more hydrogen in the star, then it's going to make it more rapidly. It goes through it faster because there is more chance for the collisions to happen between hydrogen and producing basically the final product being helium. So actually, these stars, they go through their material very fast. Whereas smaller stars, they don't have much hydrogen to begin with in their core. So their chances for collision between hydrogen and hydrogen fusing to form the heavy version of hydrogen is actually smaller. So they don't have a high rate of nuclear reactions inside their cores. In other words, they don't produce a lot of energy, which means that their surface temperature is a lot less than that of a much bigger one. So the size plays a role in here. But which means also, since there is a very unlikely chance for their hydrogen to fuse to form helium, that means that they go through their material on a very, very, very slow pace. They will outlive most of the big stars. As a matter of fact, their life cycles goes in the billions of years, much, much older than the sun. The sun is 10 billion years. These things, they can last a lot longer. Sun is an average star in every other respect. So when you look at this main sequence stars, you have a very clear understanding of what's going on. On the other side of the size of the picture, there are giant stars and there are supergiant stars that have left the main sequence stage, and they are consuming the hydrogen not inside their core, but outside of their core. As a matter of fact, they grow so much because of this much higher rate of nuclear reactions in their cores, or in their actually outer shells, not the core, the shell above the core. So in this case, their size grows because of this reactions, and especially if they start big to begin with, and they are red giants. And the reason why they are red is because the radiation, by the time it reaches the surface, the wavelength expands so much. It goes through the Compton scattering and goes into the red region. So their surface temperature is much, much lower than that of at least some of the stars on the main sequence range. And then you have even bigger than that, the supergiants, and these are usually in their final stage of their life. Okay, they only have few million years to live in that region, and then either depending on their size, they have several options to go through. If their size is like the size of the sun, they really, after they run out of fuel, if you wish, they run out of hydrogen, then in this case, gravity takes over and brings them closer and closer toward their smaller and smaller. Basically, it brings all the material. After they shed a lot of their gases, basically, after they do that, they become what is known as white dwarfs. Okay. Ceres, for example, is a binary star. One of them is actually white dwarf. Okay. So these are stars that the only reason why they are hot is because of the gravitational compression that they are going through. Okay? They retain a lot of their heat from the early life, and they're extremely hot, actually, much hotter than the some of the main sequence stars. And they are on one group by themselves, okay? So that's the fourth group, the white dwarfs, basically, and the smaller ones in there. But then there are stars that are actually bigger than the sun, which they have two possibilities. Either they keep on collapsing until at some point the gravity becomes so intense that at some point the protons, namely the hydrogen and the electrons, become so close from one another that they fuse and become neutrons. So basically, at the end of the day, what you're left with, all of the materials are gone with the exception of neutrons. And these are called neutron stars, okay? Neutron stars, they come in different classifications. The early ones are spinning so fast, and they're called actually pulsars, okay? Because of the extreme high magnetic field, because again, neutrons are magnetic, and they produce a strong magnetic field, but because of their rotation, they send signals at a regular rate. Okay, they're called pulsar because they pulsate. Okay, some of them are actually even more dramatic in their magnetic effects. They're called magnetars, but they're all basically neutron stars, super dangerous things that can cause a lot of damage if you're near them, because of their magnetic field, super strong magnetic field, and their gravitational field too, which is a very powerful stuff. And then there is a possibility if the star exceeds a certain size that it actually goes supernova, okay? In other words, it keeps on collapsing until at some point you run out of basically place to run into, because at that point gravity is so intense that there is no limit for its collapse. It goes to a singularity, and that is what we know as black holes. As a matter of fact, there are black holes abundant everywhere. There are some of the small size that form through this process, but there are some that we really don't know how they form because they are super big, super massive in their size. Like the ones in the center of the galaxies, like in our galaxy, there is in Sagittarius constellation, there is a point in it that's called Sagittarius A star. That is actually the black hole where everything in the galaxy revolves around. So it looks like this is a feature for our own galaxy, the Milky Way, but it's not unique to it. As a matter of fact, most galaxies, they have in their nucleus, in their galactic nuclei, they have a black hole, super giant black hole, not a regular black hole. And those are supermassive black holes, I should say, which means their size, like for example, for the one in the Milky Way, is several million times bigger than the sun in terms of mass. But there are even bigger than that. There are even more giant than that. Okay? Like the one, our neighbor, Andromeda, has even bigger black hole in it. Okay? So this is in a nutshell the entire chapter. So the galaxies at the end, like our own galaxy, we have the Milky Way and our neighbor. When we call it neighbor, it's 2.5 million years from here. It's very far, okay? It's called Andromeda, but we have actually two minor galaxies nearby called the Magellan Clouds. One of them is small and one of them is large, and they're only about 100,000 light years away from us. So they're, I mean, like in this scale, they're extremely close. And then you have the Triangulum, which is also another galaxy in our local group, but we have actually more than that. Okay, we have a lot of galaxies in our neighborhood. Our galaxies actually, in our local group, they form with other local groups, they form a cluster of groups, basically. And we happen to be in between two big clusters, two groups, basically, the Virgo group on one side, and there is another group on the other. And our group is actually tiny in comparison. Then you go and look at it at an even bigger scale. Okay? And now the clusters, basically, they form superclusters, and now you have groups, and the entire universe is a huge size, basically. So this is really how the entire thing is forming. Galaxies come up in three different classifications. There are galaxies like our own galaxy and that of Andromeda, which are called spiral galaxies, because they seem to be like a pancake, basically, shape, and they spin around their galactic nucleus, okay? So each one of them spins around its own. And they have a regular shape, predictable shape, and they seem to be actually in their prime life, basically, when it comes to that. And then there is elliptical galaxies. Elliptical galaxies are actually a regular shape. They must have been very old in comparison, that probably they formed from the collision of several other galaxies, and they basically have this like a spherical shape in here, okay? So that's really how they are. And then there are irregular shaped galaxies. Those are usually during a collision of two or more galaxies forming that. I mean, if you look, for example, on the Magellan clouds, both of them, the small and the large, are they elliptical or are they irregular shapes? Because at some point, if you trace back their history, we'll see that they actually collided with our own galaxy in the past, and they keep on doing that too. So in the future, they're going around the galaxy. They're actually satellite galaxies for our own galaxy. So this is an interesting stuff. Now, there is also two kinds of galaxies in terms of their activities. There are the dormant galaxies that are not active like our own galaxy. And then there are galaxies that are active galaxies. Active galaxies in two ways. First of all, in their star formations. Our own galaxy makes a star almost every month. There is a new star that is formed in it. So it's a regular star, a regular galaxy. But there are galaxies that they make stars much, much faster. They're starburst galaxies. They make galaxies on a very, very fast pace. So usually those are through a collision when the intergalactic basically gas between them, or the medium between the galaxies, or even inside the galaxy, is being compressed because of these actions. It's forming stars at a much faster rate than a normal standard galaxy. So those are the starburst galaxies. And then there is another kind of galaxies like M87, which is a galaxy that is well studied, as it has an active black hole inside of it. It's basically feeding at an extreme high rate, taking materials inside and ejecting materials from this basically feeding frenzy, if you wish, going through a lot of materials at once, so that those materials are being ejected at extreme high speeds, almost the speed of light, extremely high energetic. By the way, the M87 galaxy, we were able to even take a picture of its own black hole. So this is a confirmation of something that we suspected for a long time. So this is something that is actually, it's an ongoing topic. We're trying to understand the stuff in here. And this is one thing that we took pictures of. If you ever saw the movie Interstellar and how the black hole that they called it in the movie, I forgot what they called it now, Gargantula or something like that. Anyway, the point being in here is the theory then, this is how the black hole should look like when it bends, slides around it, and so on and so forth. And that was actually, the movie came out before we took a picture of the first black hole ever, which is from M87, the galaxy there. And that is it looked, I mean, very, very similar to even what the movie at least was saying, because actually the movie had the support of a scientist from Caltech Pasadena, Dr. Kip Thorne. So he's the one who actually helped in the movie, the making of the movie, and he told them, this is what we think the black hole should look like if you are near it, if it is active. So based on the calculations of the models and physics, this is how it should look like. Sure enough, when we took pictures in 2017 of the first black hole, it looked similar to what the predictions based on calculations predicted. So this is fascinating things. Anyway, so if we look at the sky, and I already have my program in here up and going, so I'm going to share with you that program from time to time to show you what we're talking about in here. Let me close this window in here, I don't need it. To show you how the constellations, for example, look like and everything else. So the constellations are groups of stars named over antiquity for a long time, and they're really based on culture. I showed you last time, if you guys remember, where the Polaris is, and that is actually the Big Dipper. So let me find it first of all. Let me go and share. stellarium. Okay, so again, this is the same thing that I showed you last time, with the exception I removed the, this is how this night sky look like. And this is if I am standing outside in here, looking at the east. Of course, the sun right now is bright. So what I'm going to do, I'm going to remove the ground, and I'm also removing the effects of the sun as if I have a filter running, okay, blocking the sun. This is how the night sky would look like, and I'm looking through the entire ground in here. So I'm looking through everything. What I'm going to do now, I'm going to turn on the constellations. Where is the constellations in here? Here they are. And this is where the constellations are. If you look at the north in here, this is basically where the north is. And let me remove this thing out of the way in here. Okay, this is basically Ursa Minor. This is where Polaris is. So I'm in the north in here. So let me turn on the just the sky to see that this is what the horizon would look like. So again, I am on the north in here, and this is exactly where Polaris is. This is where the northern star is. So again, this is constellation Draco. You have all kinds of constellations. One of the constellations that's super famous, and people talk a lot about, is Orion. So let me try to find where Orion is. Because right now we're during daytime, so if we go outside, we're not going to see anything, okay? So here is Orion the Hunter. This is Betelgeuse. Betelgeuse is about 600 and something light years, or how far is it? Distance is about 500 light years from us, okay? There are fluctuations numbers in here, depending on how you read about it, because it depends on actual size of Betelgeuse. Now, if you look at the Orion in here, there is these things in here which are nebula. I mean, even with the binoculars, you should be able to see them. This is one of the things that triggered Messier to look at the sky and start to classify these objects. And that's what M stands for in M87, Messier, object Messier M87, which was this seems to be like a clouds in the sky, okay? So this is basically in the night sky. So these are not definitely stars, but if I look at this one and try to zoom on it, it's between the legs of Orion the Hunter, and this is his belt, okay? So if you remember, and there is another movie actually that you guys, what is it? Men in Black, Orion's belt. So when they were referring to the belt, they were talking about the three stars, Al-Nitaq, Al-Mintaqa, and Al-Nilam. By the way, all of these things are Arabic names. Even Betelgeuse is an Arabic name, which is coming from the Arabic word Betelgeuse, which means the house or the home of the, what is that tree? I forgot even the name of the tree in here. Bellatrix is on the other side of the arm. But the point in here, if you go between the legs, and Raja stands for leg actually. So if you go between them and you start zooming, even with binoculars, you're going to see some of these clouds. This is actually starburst. This is where some of the stars are forming in here, okay? So if you look into here, this is actually a cluster of stars, a lot of stars, but this is not a galaxy. This is just within our own galaxy, because if you look at the distances in here, how do I know? The distance of this object, do I have the distance in here? Some of these ones, you don't have the distance for them because of the fact that we don't know. So this one is 2,330 light years from us. Remember, the size of the galaxy is about 100,000 light years across. So at any point, an object could be at furthest from us 50,000 light years from here. That means it's within our own galaxy. So when I mentioned the fact that the Magellan Cloud, for example, they're 100,000 light years from here, they're actually outside of the galaxy, okay? They're outside of the galaxy. And this is one of the things, and we're going to talk about this one next chapter, about how Mr. Hubble basically discovered that because up to the 1930s, we thought that our own galaxy is it. This is the entire universe. And we thought the universe was big then, about 100,000 light years across, because we can basically, based on the brightness of objects and things like that, estimate how far they are. Until Mr. Hubble looked at the Andromeda galaxy and noticed that there is a certain type of stars, okay, that we know specifically what type of frequencies they emit, the wavelength they emit, Okay, those are variable stars. So the Cepheids, they're called. He looked at the shift in the frequencies and he estimated their distance to be more than 100,000. So his initial calculation is about almost a million light years. Okay, a million light years instead of 100,000 light years. So he knew immediately that they are outside of our own galaxy. Not only that, but they are galaxies of their own. So that was really a big revolution in the view of the entire universe. All of a sudden, the universe, instead of being this big, now it's an unimaginably size bigger than what we could have thought initially, just because of those observations. Okay. So that was something that was a revelation. Anyway, we're talking about the constellations in here. This is how you find the constellation. This is Orion, the Hunter. Let me remove the sky in here because I don't want it. That means you can see it right now during daytime because this is the horizon. This is the east side. That means you're not going to be able to see it nowadays in the sky. You have to wait a few months from now or a few months in the past to see it because of the fact that the Earth is going around the sun. And that is how many constellations you can see during daytime. Unless there is a solar eclipse, which blocks the sun, then you can see Orion. So again, let me remove the horizon. Okay, so where is Taurus? Taurus is in front of him. Here it is. Okay, so this is the Taurus. This is the eye of the Taurus at Dabaran. And again, a lot of these constellations they have all kinds of stories. This is Ceres, parts of the Canis Major. So this is the hunter, this is his dog, and this is basically what he's hunting for. So there are stories that go with it. Okay, so again, that depends on the culture basically and where the background is. So let me go back into the slides in here, share. Again, I mentioned the fact that the constellations are visible only during certain times of the year because the sun is so bright during daytime, we can't see them. I mean, if we are in September and we were looking at the sky, this is how it looks like from our vantage point on Earth. Because the other constellation on the opposite to it in March, we can see it. We can't see it because the sun during daytime is blocking the view for us. When the Earth spins toward the nighttime, this is what you see. When the Earth spins facing the sun on our day, this is what we're supposed to see. But we can see it because of the sun basically blanking the entire sky with its light. Its luminosity is super high. Its brightness is super high. On our night sky, at least. During a solar eclipse, though, you can see these ones. You can see these constellations. That's fascinating. That's actually very good. Okay. Can you see that during a solar eclipse, the darkened daytime, sky would show constellation positions as normally seen 6 months from now, because 6 months from now, the Earth will be here. And then you can see this constellation during nighttime. Obviously, you can't see this one because of the sun and so on and so forth. So again, this is the Big Dipper, and it points to where the northern star is, and everything revolves around it. The thing that to note in here is that these stars are not on the same distance from us. This is, for example, if you take the Big Dipper, this star is 53 light years. That means it takes like 53 years to reach us from it. Whereas this one in here is 360 light years. Let me go back into my simulation because it's very important to see it on a practical perspective. So let me stop sharing and let me share with you the stellarium. Okay, let me move this one out of the way. So again, this is Orion. So this is Betelgeuse. Betelgeuse is a famous star. It's about 500 light years from here. And you can clearly see from its color, it's a reddish star. That means that its surface temperature is less than that of the sun, okay? And its size is huge compared to the sun, okay? Its magnitude is 0.45. That means how bright it is. This is the basically its own emission in here. And this is how much it's bright in the night sky. If I look at another star, and the distance, which is important in here, it belongs to the Orion. So when you look at this program, you see Orion. ORI, that means that it is an Orion star. If I look at any one else, okay, for example, in the top, which is about the distance is twice almost as much. It's more than, it's almost twice, 817 light years away from us. Safe, which is the Arabic word for sword. Again, this is his sword, actually. Is, how far is it, the distance? Some of the stars, you don't have all of the information. Is, what is it, 647. So in terms of distance, this is 500, this is 647, which is 150 light years is a huge distance. So this one is much, much deeper into the sky than this one, okay? And this one is even deeper than both. It's much further away. As a matter of fact, this entire 3 stars that form the belt are at different distances. This is 800 and something. This is almost 2,000 light years from here. So it's even further than all of them. And this one is, the distance is even further than the first, all of them. This is 2,000 something, this is less than 2,000. And Rigel, which is the leg of Orion, is almost as far as Nitak, okay? So those are some of, Bellatrix, for example, which is the other shoulder of, or the arm of Orion, is, where is the distance? It's only 252, so it's the closest from all of them. Did I say the Safe is closer? Yeah, the Safe is actually far, okay? So these are some of the stars. Let me look at one famous star, because that's the brightest star that you see in the sky, which is Ceres, okay? And Ceres is 8.6 light years away, which is really in our neighborhood. And it's part of a binary, as I said, okay? So this is a very, very close star. It's not the closest, though. The closest star is actually Proxima Centauri. And there are 3 stars in the Proxima Centauri. All of them, they're within 4 light years from us. So they're very close. Actually, Proxima Centauri A, Proxima Centauri B, and Alpha Centauri A and Alpha Centauri B and Proxima Centauri, they are part of our neighborhood. They are actually our closest neighbors in terms of our stars. So this is the night sky that you can see in here. Okay, so let me stop sharing. So the depth, so when you go outside and look at the stars, they are not all on the same dome. They are not on the same distance from us. Some of them are further away than others, okay? And that impacts their brightness, because the further away, the less of your light is going to arrive us basically in here. So the brightness is going to be less. So you really need to be super, super hotter temperature or some bigger star, like for example, Betelgeuse, although it's less temperature, but it's a bigger star to really produce the same luminosity. So you have a very huge light bulb that is dimmer, but when it's big, it produces a lot of light. Okay, I think I did this animation last time, basically when we zoomed in on Polaris, and we let the time evolve so fast that it allowed us to go through this and see that the stars actually form this nice formation here in the sky. This is just because of the Earth moving, rotating, that's all. It's going around its axis. That's why you see things moving in the sky. The stars are moving in the sky. The reason why you see the constellation changing for the location in the year is because of the relative motion of the Earth around the sun, yes. Okay. So hopefully you go through all of these questions. So again, I mentioned that the brightness of a star in 2 ways: apparent brightness, the brightness as it appears to us, and the luminosity is the intrinsic brightness dependent of how bright it is. So there is one of them. The luminosity of stars is compared to that of the sun. Remember, the sun delivers an amount of energy of 4. Am I sharing the screen or am I talking to you guys?
No, just about to tell you you're not sharing.
Sorry. Okay. Yeah, I just realized that I have my share screen open, but did not click on the button to share. Anyway, sorry about that. Anyway, so remember the brightness of the sun, how much energy is being transmitted. It's about Okay. It's 4 times 10 to the power 6 watts. That says basically how much energy the sun produces every second. And that is on its surface. Remember, the radius of the sun is about 700,000 kilometers. And when you square that number, obviously I have to convert it into a meter. So it's 700 million meters. When you square that number, it's a ridiculous number. Okay? It's a huge number. And multiply it by pi to find the actual area, the surface area of the sun. That's how much energy is being dumped outside in all directions. That's actually every second it's losing a huge amount of its mass because of that energy. And that is going to be, everything now is going to be compared to the sun. Because of the sheer amount of numbers that we're dealing with, so we don't really want to keep those huge numbers in our heads. So we say, okay, how bright is it compared to the sun? Or how luminous is it compared to the sun? So the luminosity is an intrinsic property depending on that point. So if I take 2 stars and put them one next to one another, that property depends on 2 factors. First of all, on the surface temperature and how big the object is. If the 2 objects have the same surface temperature, the bigger it is, the more luminous it is. So if both of them are sitting on the same temperature, let's say for both of them as 5,000 Kelvin, the smaller will emit less energy because it has less skin, if you wish, to emit it through. Whereas the bigger object has more skin to emit that in every other direction, so it should be brighter than the other one. So the size matters. And then the other factor in here is the surface temperature. Even though the object may be smaller than a bigger one, it could emit potentially more energy if in case it's even hotter, okay? So the brightness depends on these 2 critical factors, okay? The size and also the temperature. And the temperature is really a reading into the heartbeat of the star, how much energy is produced inside its inside. That is basically what the temperature is. It's like, for example, somebody fill his or her pulses. That is exactly what the surface temperature is of the star. So again, these are just discussions of the same things in here. This is the HR diagram, Hertzsprung-Russell diagram. So basically, as I said before, you have 4 groups of stars. This is the main sequence stars. And if you look inside in here, can I zoom in onto this in here? What is the slideshow from current? Can I zoom or not? No, I can't. Are you guys looking at the same thing or does it appear bigger? Okay, very good. So I don't know which screen you're supposed to be looking at, honestly, because I have 2 screens in here. There is one that has a sidebar on it and one with no sidebar, just a slide. Which one you guys are looking at? Can you tell me? With or without slide bar?
We see the one with the slide bar, the next slide.
Okay, so it's screen 1 then. Okay. Because the other one also popped at the same, something similar, except it doesn't have that. Okay, very good. So basically what you have in here, you have the main sequence stars. And the word in here is main sequence. And the stars, they range in color from the blue color, which is super hot stars, to the coolest stars in the visible range, of course. This, of course, depends on the frequencies that you look at. This is in the visible region. So the stars, they range in temperature from almost more than 30,000, 40,000 Kelvin, which is extremely high temperature. You cannot even, that's the surface, not the core. So the core must be hotter than that. It's in the billions of, in the millions of degrees, okay? Whereas the surface temperature in here is about 3,000 Kelvin. 3,000 Kelvin is when iron becomes basically, or at least when it becomes red, basically. So the sun is in here, and it's, if you look at the luminosity in here, it's 1. So this is the luminosity of the sun, and its surface temperature is around 5,000 Kelvin, 5,500 or 5,700 to be closer to the correct number, Kelvin. So this temperature, surface temperature in degrees actually in here, Kelvin, which is just shifted by 273. So when you say Kelvin, it's almost the same thing as degrees, okay? So it's around 6,000 degrees. So that is the surface temperature of the sun. And that puts it right in the yellow region. So that is what the color of the sun is. If I move on this scale, there are bigger stars in here. And if I look on the lower scale in here, these are smaller size. So look at the size also, it's bigger and hotter. And in here, they're smaller and cooler. Okay, those are the typical behavior of the main sequence stars. Our two nearest neighbors, Alpha Centauri A, is slightly hotter than the sun, slightly bigger than the sun by 20%, basically 1.2% the size of the sun. Alpha Centauri B, which is our next, which is also another neighbor in our neighborhood, is slightly less, 0.9 actually, is about 10% less than the sun, slightly cooler than the sun. So those are two of our neighbors, okay? And they form a binary that is very close from one another. And with them, there is a Proxima B, which is somewhere in this region. Its surface temperature is extremely, extremely low. It's actually a reddish star. Proxima Centauri B is actually the closest of them all to us. And the three of them, they form actually a three-star, basically, system together, all of them, because they're very close from one another. Okay, when I say very close, they're within reach from one another. Actually, Proxima Centauri B, we know that it has at least 2 planets on it. So we were able to see those planets, I mean, to calculate those planets. So this has, and actually they are in the habitable zone. The only trouble with it is being a red, being a red star in here, a red dwarf star because of its size. It has this extreme high burst of X-ray radiation, so life on those planets might not be possible. But if you were to stand on those planets or one of those planets and look at your sky, you will see a reddish star, and actually your evening and your midday actually would look similar to our evening in here in terms of the color, because of the reddish color, reddish star. So that is midday. It looks just like on an evening day or morning day in here. And you look at the sky, there is actually 2 distinct stars nearby. And you can see them during daytime if you looking up. I mean, they're not going away. So those are part of the same system, 3 stars. So those are our neighborhood, and they are all main sequence stars. And then there is the other group, which is the red giant. Now, a star, when it goes through its all of its hydrogen inside its core, then it's going to basically go through several other stages where it starts to consume hydrogen in the next layer. Actually, it's going to go through the next shell, if you wish. Okay, so at that point, it grows in size. The nuclear reaction becomes at a higher rate. And the star, basically, the only reason why star has its own size is because there is a competition between 2 forces. The gravity, which is trying to pull the star together. And then actually there is nuclear reactions, which are producing a pressure outward. So the balance of these 2 keeps the star together. That's why they're in their main sequence stage. Otherwise, if there is not enough pressure coming from the nuclear reactions, then in this case, the star will shrink in size because of gravity. If the rate of the nuclear reactions increases, then the gravity will not win. In this case, the star will grow in size, and it will grow and it will become a giant in this case. And its temperature is actually in the red region. This whole thing is the same temperature. Other stars starts big to begin with, and they don't go through the main sequence stage, and they go through a different process. And they end up, so they're giant to begin with, and they end up in a supergiant stage when they go through the next process of their life. They go very fast during their through their fuel, basically through their hydrogen. The lifespan of these stars, all of them actually, is a lot smaller as you move along in this line on the main sequence star. Stars live longer on the main sequence in here. So these stars are very young, relatively speaking, and they go through their lifespan very quickly, and they become supergiants when they're in their final stages. At any rate, this ones, most likely, they will end up to being supernova. Okay? Or depending on their size, or a neutron star. Okay, this one's also will end up with that. For the most part, depending on where they start from, either they are going to go into a neutron star, or if they are coming from this side in here, like the sun and below, or at least slightly bigger than the sun and below. In this case, actually, they go through the giant stage, but then after they run out of fuel, basically at that point, there is no reason for them to keep, there is no outward pressure due to nuclear reactions. So in this case, it starts to shrink due to gravity, and it goes rapidly through other stages of nuclear reactions, basically converting heavy elements like helium into lithium, and lithium into beryllium, and beryllium into other elements, until they form carbon. The carbon provides a layer in there, sometimes even oxygen, and now they start to cool down, okay? And they end up in this size in here. And they end up, depending on how old they are, if they are new, they are going to be super hot because of this conversion of the potential energy due to gravity into heat in this case. So they're going to be super hot, and they start moving down on the scale in here with their temperature basically cooling down, okay? The universe is not old enough, at least for us to see where these things end, but most likely they will run out of completely energy down the road. But these ones, we know how they end. They end violently into either a neutron star or actually into a supernova. Supernova, there are two types of them. So this is basically in a nutshell what's going on. Okay, let me escape this thing in here because I don't even know how this slide is not working. Are we back into the same point where we started from before doing this? Yes? Okay, very good. So this is the story basically of all of the stars and how they evolve. Hopefully you guys go through those things. So this is the life cycle basically of the star. So it begins as a nebula, because as the star sheds its materials, now it becomes, those materials becomes basically a source for the next star. The first generation stars are the ones that formed immediately after the universe, and some of them are actually still in first generation star because of their size, small size. And others, they go through several stages, like we know that the sun is not the first generation star. Case in point, we're here. Iron was formed, and it must have formed and heavier elements must have formed into a supernova. There is no way for a star to get these materials in it, like for example on planet Earth, if we did not have a supernova before this. So again, the nebula starts to coalesce together until its temperature is high enough so that it becomes a protostar, and then it goes into the stage of becoming nuclear, expelling all of the gas that was there, forming the other planets basically, and make them cease to increase in size. And then it goes through the life cycle I described earlier in the HR diagram, depending on how it started. It could end up in one of several scenarios, depending on where it is in the life cycle. So a white dwarf cools for eons until it is too cold to emit light. If part of a binary, now if it is part of a binary, like for example Sirius, we know that there is a white dwarf in there, and there is actually Sirius, the big star A. So now there is actually, it's feeding off of its neighbor of the binary, and this one starts to grow now in size. Okay. Once it grows big enough, now remember it was big to begin with, it's going to actually cause it to go nuclear, and actually at that point it's going to go of a different type of supernova. Okay. In 1054, in July 4th, 1054, the Chinese noticed, at least in their documentations, they documented that there is a star that has formed, and that star was so bright that it could be seen during daytime for several days. Basically, you could see it during daytime. And it's actually in the Japanese also literature, they talked about this one too. Okay, so later on in the 1700s, there were, of course, astronomers looking at the sky, and the Crab Nebula was discovered. Okay. And it was named as such because when the initial drawing looks like a crab, basically. So later on, studies showed, when you take several pictures of it over a few years, that its size is actually growing. So if you go back and redraw its size back to its starting point, it coincides with that event that was documented in Chinese literature. So indicating that this is exactly the star that has formed. So this is the first, if you wish, supernova, and it's the most heavily supernova studied. Let me share with you the screen again that I was on share. It's interesting when you are looking at studying these objects to find them in the sky. Again, let me find where search for the Crab Nebula. I already looked for it earlier. So this, you cannot see it with your naked eye, but with binoculars, and I'm going to do that when it's visible in the night sky next time. I have my own binoculars, actually. These are very nice binoculars. They're very cheap, by the way. Binoculars are not expensive. It's like $60, $70. So this is 380 by 100. So this should be perfect for that. So you can see it with binoculars. So again, I'm zooming on it, and here how it looks like. If you look inside of it, and I don't know if we can look inside, there is actually a neutron star, okay, which is about 20 miles across, okay? But that's the one that the Chinese literature referred to forming, okay? For a few days, it was bright, and then it started to lose its dimness over the next, basically, 1,000 years now or so, okay? So this is the same one. Let me stop sharing that screen and share. Well, let's look at the size of the stars. The sun, and it's a very interesting thing to go and look at all of these objects, okay? Vega is not a faraway star. It's about 25 light years from here, and it's a big star. Okay, as a matter of fact, the story of Vega is similar to Polaris. The sun right now in the northern sky is Polaris. 25,000 years ago, or is it not? About 13,000 years ago, actually Vega was. So right now we look at Polaris. It's in the northern sky, and actually our axis, the tilt axis, is actually changes locations. It's not always pointing toward Polaris. Right now it's pointing Polaris, but there is a precession actually for the tilt of the axis of the Earth. At some point, it's not going to be pointing anywhere. But then, at least into a big star that we can name. But later on, about 13,000 years from now, it's going to be pointing, or 12,000 years from now, it's going to be pointing toward Vega. So that is the star in here. But look at the size of it compared to the sun. It's much bigger than the sun. Now, that is dwarfed by Arcturus, which is an even bigger star. And all of this are actually in our Milky Way. All of the stars are in here, in our neighborhood somehow, okay? Arcturus, which is a red giant, is even smaller than Alpha Ceti, okay? Which is even a red giant. Look at the sun now. It looks like a small, tiny planet compared to all of these things, okay? Now, Betelgeuse, which I mentioned several times in here, about 500 light years from here, it's even bigger, which is a red supergiant, okay? If you take the entire sun, it becomes a dot in Betelgeuse. Betelgeuse, by the way, we're monitoring it because we're expecting it to go supernova, I mean, anytime, probably within the next 100,000 years or so, okay? Which is a very short period of time, basically. Obviously, we may not be here to witness it, but it could have gone supernova and wouldn't know until 400 years later or 500 years later, okay? Anyway, Cepheid A, which is a red giant, is probably the biggest, one of the largest stars in the galaxy. And the sun, now you cannot even see it. Vega becomes a negligible, basically, dot in here. And even Betelgeuse becomes tiny compared to this hypergiant stars, okay? This is about 3,000 light years from here in the Milky Way, of course. So when you see 3,000, 5,000, 7,000, and even 25,000, that means you are here. You are within our own galaxy. And I mentioned the black holes that form from supernova, but they also can exist in the center of galaxies that at this point we really don't know how they would have formed. There are some competing theories on how they formed. Probably the collapse of gases, huge masses of gases immediately into, instead of going through a star and all of the stages, go straight into a black hole stage. So again, this is how the black holes form. When you are very close from them, again, they become so big in here. I mean, they reduce in size and gravity becomes so intense. Okay, this is some of the pictures that you look at into the night sky. It would be nice if you go to a desert and look at the sky and you see this trace. This is the Milky Way. This is actually the galactic center of the Milky Way. You can look for Sagittarius A star, and that is where the center of our own galaxy is. I mentioned the fact that there are 3 types of galaxies: spiral galaxies, irregular shaped galaxies, and elliptical galaxies. M87 is an elliptical galaxy, and this is the one that we took its pictures. And then we have the Magellanic Clouds, which both of them are irregular shapes. Okay. And then we have the spiral galaxies like our own. They are distinguished by these specific arms that are going around, and the arms have names, and that is probably where most of the gas is being compressed, and that is where most of the stars are being formed also. Our sun is in one of those arms. Okay, some galaxies are known as active galaxies, and because they have 2 types of activity, is a starburst, making a lot of stars at a very high rate, or because their nucleus is actually super active because they have a black hole that is super active in here. I already mentioned M87 when we took pictures of it. Look at this, basically material that is being ejected from the center of the galaxy. Again, starbursts, they're forming stars at extreme high rates. And this is M87, which we were able to take a picture of its own black hole. This is our local in here, or cluster, our local group in here. Again, the main players are actually the Milky Way, Andromeda, Triangulum, which is actually not very close, actually, from, again, don't forget about the depth, from Triangulum. Galaxy, our Milky Way and our Andromeda galaxy, they are actually approaching one another. And they're approaching one another. At some point, they will fuse. There are 2 centers they will fuse. Okay. As a matter of fact, new studies show that the extent of the Milky Way galaxy and that of the Andromeda galaxy is much, much larger than what we thought. And they're actually already in the process of being colliding. Their outer edges are colliding in such a way that we noticed there is a high rate of formation of stars because of the 2 gases basically coming together. The Magellanic Clouds, they are here. And the other one is not too far from it. And then there are smaller galaxies in our group. If you take our local group, this is a local supercluster. So this distance from here to here is 100 million years. From here to here, it's about 100 million years. So this one is about basically a billion years from side to side. So there is a Virgo, there is Eridanus in here cluster, and those are big groups of stars. Look at the voids in here, where there is hardly any galaxy whatsoever. So the universe has a lot of voids in it too, which are mysteries, trying to understand what does that mean, okay? And if you look at even a larger scale, our network of superclusters, again, you see a lot of voids in here, and all of this, what looks like it's painting, is actually a huge amount of galaxies, and each one of them has hundreds of billions of stars in it. And this is the observable universe. This is everything that we know about the universe, that we can see about the universe, because what we don't see beyond this point, let's leave it to chapter 28 for discussion on that topic. Anyway, so this is your entire chapter. And again, there is no discussion points. Let me stop sharing I stopped sharing. Let me stop recording, and there will be, we will meet again on Thursday, okay? I mean, Tuesday, I'm sorry, next week, okay? Because we still have one more chapter to discuss these things. Good? Very good. Let me stop sharing. I'm going to stop.